Hello, everyone. I hope you are settled comfortably. Take a moment to relax, adjust your posture, and let your mind prepare for the journey ahead. Just a few seconds to breathe and arrive fully in this space. Today, we will explore galaxies. We will look at what they are, how they form, the different types, their immense sizes, and the remarkable processes that happen within them. From the smallest dwarf galaxies to the vast spiral giants, each one holds a story spanning billions of years. Galaxies are not simply collections of stars. They are dynamic systems bound together by gravity, containing stars, gas, dust, and an invisible component we call dark matter. They can host billions or even trillions of stars, along with planetary systems, nebulae, and sometimes massive black holes at their centers. The universe is filled with them, each unique in shape, size, and history, forming a grand cosmic tapestry that stretches across unimaginable distances. Spiral galaxies, like our own Milky Way, have a flat disk with sweeping spiral arms that rotate slowly around a central bulge. These arms are often bright and full of young stars, forming in clouds of gas that glow in vivid colors. The central bulge contains older stars and usually surrounds a supermassive black hole at the center. Stars within the disk orbit the center in organized patterns, creating the familiar rotation curves that astronomers study to understand the galaxy's mass and structure. Elliptical galaxies are more uniform and often appear as smooth, rounded shapes. They contain older stars and less gas, which makes them less active in forming new stars. These galaxies often form from the mergers of smaller galaxies, which can scramble stars into dense elliptical arrangements. Despite their seemingly simple appearance, many elliptical galaxies are massive, dominating their regions of space with trillions of stars. Irregular galaxies, by contrast, lack a defined shape. Their forms can seem chaotic as a result of interactions or collisions with other galaxies. Within these irregular systems, star formation occurs in concentrated pockets, while older stars are scattered more evenly. Observing irregular galaxies offers insight into the ongoing dynamic processes that shape galaxies throughout cosmic time. The size of galaxies varies dramatically. Dwarf galaxies may host a few billion stars, while giants can have over a trillion. Spiral galaxies like the Milky Way are considered large, with roughly 100 billion stars. Some supergiant galaxies stretch over 1 million light-years across, dwarfing their smaller neighbors. Despite these differences, all galaxies are held together by gravity, including the unseen influence of dark matter, which forms halos around their visible components. Galaxies evolve over billions of years. They form from the collapse of matter in the early universe, with gas clouds condensing into the first stars and star clusters. Over time, these clusters merge, forming larger systems. Galaxies grow through star formation, accumulation of gas, and interactions with other galaxies. Collisions and mergers are common, dramatically reshaping structures and often triggering bursts of new stars while feeding central supermassive black holes. Within galaxies, the motion of stars and gas is governed by gravity. Spiral galaxies have relatively orderly stellar orbits, while ellipticals show more randomized motion, reflecting their turbulent histories. These motions provide strong evidence for the presence of dark matter, which, though invisible, shapes the dynamics of galaxies. Supermassive black holes are found at the centers of many galaxies, with masses ranging from millions to billions of times that of the Sun. These black holes interact with surrounding gas, sometimes forming luminous accretion disks and jets. Active galactic nuclei, powered by matter falling into these black holes, emit energy across the spectrum, from radio waves to X-rays, revealing the dynamic and energetic nature of galactic cores. Galaxies also exist in groups and clusters, bound by gravity and often interacting. These clusters can contain thousands of galaxies, influencing each other through tidal forces, while vast filaments of dark matter and diffuse gas form a cosmic web connecting galaxies across millions of light years. By observing galaxies, we glimpse the history of the universe. Distant galaxies allow astronomers to look back in time, showing how structures formed and evolved over billions of years. Studying their shapes, motions, and interactions helps us understand star formation, the growth of black holes, and the evolution of cosmic structures on the grandest scales. Galaxies are vast, complex, and dynamic. They are living records of cosmic history, showcasing the interplay of gravity, matter, and energy. By exploring them, we understand not only the universe outside, but also the processes that made our own Milky Way, our solar system, and even the atoms in our bodies possible. Galaxies are born in the early universe, not as fully formed structures, but as clouds of gas and dark matter slowly coming together. Imagine vast regions of space, almost empty, where gravity pulls material toward denser areas. These regions gradually collect gas, forming the first stars. The earliest galaxies were small and irregular, often only a few thousand light years across, compared to the hundreds of thousands of light years of modern giants. As stars form within these primordial clouds, they emit light and heat, shaping their surroundings. Massive stars live short, brilliant lives, exploding as supernovae and dispersing elements like carbon, oxygen, and iron into space. These elements are the building blocks for future generations of stars, planets, and even life. Each galaxy carries within it the history of countless stellar generations, a record written in the stars themselves. The formation of larger galaxies is often driven by mergers. Small galaxies collide and combine, their stars, gas, and dark matter mixing together over millions of years. These events can create spectacular structures. Spiral galaxies often result from such interactions, with gravitational forces organizing stars into sweeping arms. Elliptical galaxies, on the other hand, can form when collisions are more violent, scrambling stars into dense, smooth distributions. Galaxies vary not only in shape, but also in composition. Some are rich in gas and dust, allowing new stars to continue forming. Others, like many elliptical galaxies, have used up or lost most of their gas, and their star formation slows dramatically. In these older galaxies, the stars are ancient, redder, and cooler, shining quietly in the absence of new light. Observing these differences tells astronomers about the evolutionary history of galaxies, revealing which have experienced calm growth and which have endured violent interactions. The scale of galaxies is staggering. The Milky Way, our own galaxy, is roughly 100,000 light-years across, containing over 100 billion stars. Some of the largest known galaxies, called supergiant ellipticals, can exceed 1 million light-years in diameter, containing trillions of stars. Yet galaxies exist in all sizes. Dwarf galaxies may be only a few thousand light-years wide, sometimes orbiting larger galaxies like satellites, influenced by their gravitational pull. Within a galaxy, stars are not stationary. They orbit the galactic center in paths determined by gravity. In spiral galaxies, these orbits create the familiar flat disk structure, with stars moving in nearly circular paths. Elliptical galaxies show a more chaotic motion, reflecting the turbulent history of stellar mergers. These movements reveal the presence of dark matter, which dominates the mass of a galaxy, even though it cannot be seen directly. Dark matter forms a halo that surrounds the visible stars, holding the galaxy together and influencing its rotation. Many galaxies contain a supermassive black hole at their center. These objects can be millions to billions of times the mass of our Sun. While often invisible, their gravitational influence shapes the orbits of nearby stars. When gas and dust fall into a black hole, they form a glowing accretion disk, sometimes producing jets of energy that extend far into space. Active galaxies, such as quasars, are powered by these processes and can outshine all the stars in their host galaxy combined. Galaxies also do not exist in isolation. They are part of larger structures called groups and clusters, where gravity binds dozens, hundreds, or even thousands of galaxies together. Within clusters, galaxies interact, sometimes exchanging stars and gas, influencing each other's evolution. On even larger scales, galaxies trace the cosmic web, connected by filaments of dark matter and gas that stretch across hundreds of millions of light-years. These large-scale structures show that galaxies are part of a universe that is interconnected, dynamic, and constantly evolving. Studying galaxies allows us to look back in time. Light from distant galaxies takes billions of years to reach us, so observing them is like seeing the universe as it was long ago. By comparing nearby galaxies with those far away, astronomers can trace how galaxies grow, merge, and change over cosmic time. Some galaxies in the early universe are surprisingly small and irregular, while others show surprisingly mature structures, already forming disks and bulges only a few billion years after the Big Bang. Galaxies also host an incredible variety of phenomena. Star clusters, nebulae, supernova remnants, and molecular clouds all reside within them. Spiral arms glow with hot young stars, while central bulges contain old reddish stars. Some galaxies have rings, bars, or streams of stars that trace the gravitational influence of past interactions. Each galaxy is a laboratory of cosmic physics, offering clues about how matter, energy, and gravity interact on grand scales. Through all these observations, a picture emerges of galaxies as complex, evolving systems, alive with the processes of star formation, stellar death, and the slow dance of gravity. They are both islands in space and part of a larger cosmic structure, reflecting billions of years of growth and change. By studying galaxies, we understand the history of the universe, the life cycles of stars, and the forces that shape everything, from the smallest atoms to the largest cosmic structures. Galaxies come in a remarkable variety of shapes and structures, each revealing a different aspect of their history and evolution. The most familiar type is the spiral galaxy. Spirals, like the Milky Way, have a flat, rotating disk where stars orbit the galactic center in organized paths. The disk is often marked by sweeping spiral arms, which are regions rich in gas and dust, glowing with the light of newly formed stars. The central bulge is a dense, spherical region, often home to older stars, and typically contains a supermassive black hole. The spiral arms are not static. They are waves of density moving through the disk, compressing gas and triggering star formation. This process creates patterns of bright young stars, nebulae, and clusters that follow the spiral structure. Some spirals have bars, elongated features of stars stretching across the central bulge. Barred spirals are common in the universe, and the bar itself can funnel gas toward the center, feeding star formation or the central black hole. Elliptical galaxies, in contrast, appear smoother and less structured. They range from nearly spherical shapes to more elongated forms. These galaxies generally contain older stars and little gas, which limits new star formation. Many ellipticals form from mergers of smaller galaxies. When two galaxies collide, the stars are scattered into a dense elliptical configuration, while the gas may trigger brief bursts of star formation before being consumed or expelled. Some of the largest galaxies in the universe are ellipticals, dominating the cores of galaxy clusters with trillions of stars. Irregular galaxies lack a clear structure. Their chaotic appearance often results from interactions or collisions with other galaxies. Despite their disorderly forms, irregular galaxies can be rich in gas and actively forming stars. Observing these galaxies helps astronomers understand the ongoing processes of galaxy evolution, as they are often snapshots of dynamic, turbulent environments. Dwarf galaxies are the smallest in the universe. They may contain only a few billion stars orbiting larger galaxies like satellites. Despite their small size, dwarf galaxies are important for understanding galactic formation and evolution. Many of the Milky Way's neighbors are dwarf galaxies, including the large and small Magellanic Clouds. These small galaxies can be stripped of gas or stars as they orbit larger companions, slowly changing their structure over time. The composition of galaxies varies significantly. Some are dominated by young, hot stars emitting blue light, while others host primarily older, cooler stars that appear red. Gas and dust within galaxies are the raw materials for star formation. Molecular clouds collapse under gravity, forming new stars over millions of years. Supernova explosions and stellar winds then return material to the interstellar medium, enriching it with heavier elements, which become the building blocks for future generations of stars and planetary systems. Within all galaxies, dark matter plays a crucial role. Though invisible, dark matter accounts for most of the mass in a galaxy, forming a halo that surrounds the visible stars. Its gravitational influence stabilizes galaxies, shaping their rotation curves and maintaining the integrity of their structures. Observing how stars move within galaxies provides strong evidence for the presence of dark matter, even though we cannot see it directly. Central supermassive black holes are another common feature. These objects have masses ranging from millions to billions of times that of the Sun. When gas and dust fall into these black holes, they can emit tremendous amounts of energy, creating active galactic nuclei, quasars, or relativistic jets that extend far beyond the galaxy itself. The interaction between a galaxy and its central black hole influences the evolution of both, regulating star formation and the growth of stellar populations over billions of years. Galaxies are also not isolated. Most are found in groups, clusters, or even larger structures called superclusters. In these environments, galaxies interact gravitationally, sometimes merging, sometimes merely exchanging stars and gas. These interactions can distort shapes, trigger star formation, and lead to the creation of tidal streams, trails of stars stretching across space. Large-scale observations reveal a cosmic web, with galaxies and clusters connected by filaments of dark matter and diffuse gas, forming the grand architecture of the universe. Studying the diversity of galaxies helps astronomers understand the complex processes that shape the cosmos. From spirals with their graceful arms, to ellipticals with their ancient stars, to irregulars and dwarfs revealing dynamic change, galaxies are laboratories of cosmic evolution. They show us how stars are born, live, and die, how matter and energy interact, and how the universe grows and transforms over billions of years. Galaxies exist across an incredible range of sizes and masses, each reflecting the history of the matter that formed it. Small dwarf galaxies may contain only a few billion stars, while the largest known galaxies, supergiant ellipticals, can hold trillions. The Milky Way, our home galaxy, is an average-sized spiral, about 100,000 light-years across, containing over 100 billion stars. Yet even this scale is difficult to comprehend. A single light-year measures almost 10 trillion kilometers, so the distance from one edge of the Milky Way to the other is truly immense. The age of galaxies varies widely. Many galaxies formed in the first billion years after the Big Bang, over 13 billion years ago. These early galaxies were often small and irregular, made up of the first generation of stars, composed mostly of hydrogen and helium. Over time, galaxies grew by merging with others, accumulating gas, and forming new stars. Observing distant galaxies allows astronomers to look back in time, seeing these ancient structures as they existed billions of years ago. Light from a galaxy 10 billion light-years away shows it as it was 10 billion years in the past, a powerful reminder of the vast scales of both space and time. Galaxy evolution is a slow, continuous process. Stars form, live, and die, enriching their surroundings with heavier elements. Gas clouds collapse to form new stars, while supernova explosions spread enriched material across the galaxy. Collisions and mergers with other galaxies reshape structure, triggering bursts of star formation or creating smooth elliptical galaxies from previously spiral systems. Even small interactions can create tidal tails, streams of stars pulled from one galaxy to another, leaving subtle traces of past encounters. Massive galaxies tend to evolve more quickly. They exhaust their gas supply faster, leaving older stars behind. Smaller galaxies can continue forming stars for billions of years, slowly transforming their appearance. Observing galaxies of different masses and ages across the universe allows astronomers to piece together a timeline of galaxy evolution. Each galaxy becomes a chapter in the story of cosmic history, showing how matter organizes, transforms, and persists over time. Dark matter is a fundamental part of galaxy evolution. Though invisible, it forms halos around galaxies, providing gravitational support that helps them hold together. Without dark matter, galaxies would not have enough mass to remain stable, and their structures would disperse. Observations of rotation curves, where stars orbit faster than expected in the outer regions, provide strong evidence for dark matter's presence. Its influence is subtle but essential, shaping how galaxies grow, merge, and interact over billions of years. Supermassive black holes at the centers of galaxies also influence evolution. These black holes grow as gas and stars fall into them, emitting energy in the process. The feedback from these central engines can regulate star formation, heating surrounding gas, or expelling it from the galaxy entirely. In this way, black holes are not just passive observers, but active participants in shaping galactic evolution. Galaxies live in environments that affect their development. Many are found in clusters bound by gravity, where interactions are common. In dense environments, gas can be stripped from galaxies, halting star formation and leaving behind older stellar populations. In more isolated regions, galaxies may evolve more slowly, retaining their gas and continuing to form stars. This environmental influence adds another layer of complexity to the life cycle of galaxies. Despite the vast differences in size, shape, and environment, all galaxies share a common feature. They are the product of cosmic time, energy, and gravity acting over billions of years. Their stars, gas, dust, and dark matter tell a story of formation, growth, and change. By studying galaxies, astronomers gain insight not only into the history of the universe, but also into the forces that govern the evolution of matter on the largest scales. The study of galaxies is, in essence, a study of cosmic history. Each galaxy, whether small and irregular or enormous and elliptical, is a record of time, energy, and transformation. Observing these structures, measuring their stars, mapping their gas, and tracing their movements, we uncover the processes that have shaped the universe from its earliest moments to the present. Galaxies are not static. They are alive with motion, interaction, and change, offering a quiet yet profound testimony to the passage of cosmic time. Galaxies are more than collections of stars. They are dynamic ecosystems with stars, gas, dust, and dark matter interacting in complex ways over billions of years. Stars are the most visible components. They come in many sizes, temperatures, and lifespans. Massive stars burn brightly and live short lives, sometimes just a few million years, while smaller stars, like red dwarfs, burn slowly and can persist for tens of billions of years. These stars populate different regions of a galaxy, creating layers of age and color that reveal the galaxy's history. Gas is another essential ingredient. Galaxies contain vast clouds of hydrogen, helium, and trace heavier elements, often forming molecular clouds where stars are born. These clouds can be enormous, stretching across hundreds of light years, dense in some regions and diffuse in others. Within the spiral arms of a galaxy, these clouds are concentrated, compressed by density waves that move through the disk. This compression triggers star formation, where gravity pulls gas together until nuclear fusion ignites, giving birth to new stars. Dust is less abundant than gas, but plays a crucial role in shaping galactic light and chemistry. Dust grains are tiny particles composed of carbon, silicon, and metals formed in the atmospheres of dying stars or in supernova explosions. Dust absorbs and scatters light, creating dark lanes in spiral galaxies and glowing when heated by nearby stars. It also provides surfaces for chemical reactions, enabling complex molecules to form, which can eventually contribute to planet formation. The interplay of stars, gas, and dust creates a galaxy's visible structure. Spiral galaxies are shaped by the distribution of young stars and star-forming regions along their arms. Elliptical galaxies appear smoother, with older stars dominating, but their pasts often include periods of intense star formation and mergers that distributed gas and stars into a more uniform shape. Irregular galaxies display chaotic arrangements, where interactions or internal turbulence have scattered stars and clouds across the galaxy. Star formation is not constant. Galaxies undergo cycles of activity and dormancy. During starburst phases, triggered by collisions or accretion of gas, galaxies produce stars at rates far above average. These bursts enrich the surrounding medium with heavier elements through supernova explosions, creating a feedback loop that can either trigger more star formation or inhibit it by heating and expelling gas. Over billions of years, these cycles determine the galaxy's chemical composition, stellar populations, and overall evolution. Within galaxies, stars rarely form alone. Most stars are born in clusters, gravitationally bound groups of hundreds or thousands of stars. These clusters can remain intact for millions of years before dispersing into the galaxy, spreading their enriched material. Open clusters populate spiral arms, while globular clusters, dense spherical groups of older stars, orbit the galactic center in the halo. Globular clusters are among the oldest objects in a galaxy, often providing a window into the early universe. Galaxy rotation shapes the motion of stars, gas, and dust. In spiral galaxies, stars orbit the center at high speeds, with rotation curves revealing the presence of dark matter halos that provide additional gravitational support. Gas clouds follow similar paths, colliding and compressing in spiral arms to ignite star formation. In elliptical galaxies, stars move in more random orbits, contributing to the smooth, rounded appearance and indicating a history of mergers and dynamical interactions. Supernovae are critical in galactic ecosystems. When massive stars explode, they release energy and heavy elements, enriching the interstellar medium. This feedback affects nearby gas clouds, triggering new stars or dispersing material. Over billions of years, repeated cycles of star birth and death shape the chemical and structural evolution of a galaxy, providing the raw materials for planets, complex molecules, and potentially life. Even the faintest galaxies, dwarfs with only a few billion stars, exhibit these processes on smaller scales. Gas flows, star clusters, and chemical enrichment occur within them, demonstrating that the same principles govern galaxies of all sizes. Studying these small galaxies gives insight into fundamental galactic physics and the early stages of galaxy formation. Galaxies are alive in their motion and transformation. Stars shine and die, gas flows and condenses, dust drifts and glows, and the invisible dark matter scaffolds everything. Observing these processes across billions of years allows astronomers to understand how galaxies maintain balance, grow, and evolve, creating the diverse universe we see today. Not all galaxies shine in the same way. While most galaxies emit light primarily from their stars, some produce enormous amounts of energy from their central regions. These are known as active galaxies. Their unusual brightness does not come from stars alone, but from processes occurring near a supermassive black hole at their core. At the center of most galaxies lies a supermassive black hole. In many cases, this black hole is quiet, influencing its surroundings only through gravity. But in active galaxies, large amounts of gas and dust fall toward the black hole. As this material spirals inward, it forms a rotating structure called an accretion disk. Friction and gravitational forces heat the disk to extreme temperatures, causing it to emit intense radiation across the electromagnetic spectrum. This process can release more energy than all the stars in the galaxy combined. The galaxy then becomes an active galactic nucleus. Depending on viewing angle, energy output, and surrounding material, these objects appear in different forms, including quasars, ciphered galaxies, and radio galaxies. Quasars are among the most luminous objects in the universe. They can be seen across billions of light years, meaning we observe them as they existed in the early universe. A single quasar can outshine an entire galaxy of hundreds of billions of stars. Despite their brightness, quasars are compact, with most of their energy originating from a region no larger than our solar system. Their immense power makes them valuable tools for studying the distant universe. Radio galaxies emit powerful jets of charged particles that extend far beyond the visible galaxy. These jets travel at nearly the speed of light, stretching across hundreds of thousands or even millions of light years. They interact with surrounding gas, shaping the environment of galaxy clusters and influencing how matter is distributed on large scales. Though invisible to the naked eye, these jets are easily detected with radio telescopes. Active galaxies are not permanent states. A galaxy may switch between active and quiet phases depending on the availability of material near its central black hole. When gas is abundant, activity increases. When the supply is exhausted or expelled, the galaxy gradually returns to a calmer state. This cycle may repeat multiple times over a galaxy's lifetime. The energy released by active galactic nuclei plays a crucial role in galaxy evolution. This energy can heat surrounding gas, preventing it from cooling and forming new stars. In some cases, it can drive gas out of the galaxy entirely. This process, known as feedback, helps explain why many massive galaxies stop forming stars relatively early in their history. Observations suggest a close relationship between the mass of a galaxy's central black hole and the mass of its stellar bulge. This indicates that black holes and galaxies grow together, influencing each other over billions of years. Rather than being destructive anomalies, black holes are integral components of galactic systems. Active galaxies also serve as cosmic beacons. Their bright emissions allow astronomers to probe the early universe, study intergalactic gas, and trace the distribution of matter across vast distances. By analyzing the light from quasars, scientists can detect absorption signatures from gas clouds lying between the quasar and Earth, revealing the structure of the universe on large scales. Despite their extreme nature, active galaxies follow the same physical laws as quieter ones. Gravity, angular momentum, radiation, and magnetic fields govern their behavior. What differs is the scale and intensity of these processes. In active galaxies, familiar physics operates under extraordinary conditions. By studying active galaxies, astronomers gain insight into the most energetic processes in the cosmos. These systems show how matter behaves near black holes, how galaxies regulate their growth, and how energy shapes cosmic environments. They remind us that galaxies are not only collections of stars, but also engines of powerful physical phenomena, capable of influencing space far beyond their visible boundaries. As we continue, let's take a calm step back and look at galaxies in a broader sense. Galaxies are not just collections of stars. They are complex systems shaped by gravity, time, and motion. Each galaxy contains stars, gas, dust, planets, and a large amount of something we cannot directly see, called dark matter. When we observe a galaxy, we are not seeing a single moment in time. We are seeing a long history compressed into light. Some of the light reaching us today began its journey millions or even billions of years ago. Galaxies vary enormously in size. Some contain only a few million stars. Others, like giant elliptical galaxies, contain trillions. To put that into perspective, our own galaxy, the Milky Way, contains roughly 100 to 400 billion stars, and it is considered a fairly typical large spiral galaxy. Spiral galaxies are among the most familiar shapes in astronomy. They have flat, rotating disks with spiral arms extending outward from a central bulge. These arms are not fixed structures. They are regions where stars form more actively, glowing brightly as gas clouds collapse and ignite new suns. The Milky Way is a spiral galaxy. We live inside its disk, about 2/3 of the way out from the center. Because of this position, we see the galaxy as a soft, glowing band across the night sky. That band is the combined light of billions of distant stars, blurred together by distance. elliptical galaxies are very different. They are more rounded or stretched, without distinct arms or disks. Their stars move in many directions rather than following a clear rotation pattern. Most elliptical galaxies contain very little gas or dust, which means they form very few new stars today. These galaxies are often very old. Their stars tend to be redder, cooler, and longer-lived. In a sense, elliptical galaxies are quieter places. They shine steadily, without the dramatic bursts of star formation seen in spirals. There are also irregular galaxies. These do not have a clear shape. They may look distorted, stretched, or chaotic. Many irregular galaxies are the result of gravitational interactions, close encounters, or collisions with other galaxies. Galactic collisions are slow, quiet events. Despite the word collision, individual stars almost never crash into one another. The distances between stars are simply too vast. Instead, gravity gently reshapes the galaxies over hundreds of millions of years. When galaxies interact, their shapes stretch and warp. Gas clouds compress, triggering waves of star formation. New stars light up regions that were once dark. Over time, two galaxies may merge into one larger system. This process has happened many times throughout the history of the universe. In fact, our own Milky Way has grown by absorbing smaller galaxies. Even today, it is slowly merging with nearby dwarf galaxies that orbit around it. Far in the future, the Milky Way will collide with the Andromeda Galaxy. This event will unfold over billions of years. The result will likely be a single, larger elliptical galaxy. By then, the night sky from Earth, if Earth still exists, would look very different. At the center of almost every large galaxy lies a supermassive black hole. These black holes can have masses millions or billions times greater than the Sun. Despite their size, they occupy a region smaller than our solar system. Most of the time, these central black holes are quiet, but when gas and dust fall toward them, they can become extremely active. The infalling material heats up and releases enormous amounts of energy. Active galactic nuclei are among the brightest objects in the universe. Some shine brighter than the combined light of all the stars in their galaxy. Quasars, a type of active galactic nucleus, can be seen across billions of light years. These energetic centers influence their galaxies deeply. They can heat surrounding gas, slowing or even stopping star formation. In this way, black holes help regulate the growth and evolution of galaxies themselves. Galaxies do not exist alone. They gather in groups and clusters, bound together by gravity. Our Milky Way is part of a small group called the Local Group. This group contains more than 50 galaxies, most of them small and faint. Galaxy clusters are much larger. They can contain thousands of galaxies all orbiting a shared center of mass. Between the galaxies lies hot, thin gas that emits X-rays. This gas contains more mass than all the galaxies combined. Even larger than clusters are vast structures called superclusters. They form a web-like pattern across the universe. Galaxies trace long filaments, separated by enormous empty regions called cosmic voids. When astronomers map the universe on the largest scales, it resembles a sponge or foam. Dense regions of galaxies surround great empty spaces. This structure emerged naturally as gravity amplified tiny density differences after the Big Bang. Galaxies are ancient. The first ones formed just a few 100 million years after the universe began. They were smaller, more chaotic, and rich in gas. Over time, they merged, grew, and evolved into the diverse systems we see today. When we study distant galaxies, we are looking back in time. The farther a galaxy is, the younger it appears. This allows astronomers to reconstruct the history of galaxy formation step by step. Modern telescopes do more than collect visible light. They observe radio waves, infrared light, ultraviolet radiation, X-rays, and gamma rays. Each wavelength reveals a different aspect of galactic life. Infrared light shows cold gas and dust, where stars are forming. X-rays reveal hot gas and violent processes near black holes. Radio waves trace large magnetic structures and ancient supernova remnants. Together, these observations give us a fuller picture of what galaxies truly are, not static islands of stars, but evolving systems shaped by gravity, energy, and time. Galaxies remind us that the universe is dynamic. Change happens slowly, over scales that stretch beyond human experience. Yet the laws governing these systems are simple and consistent. As we continue exploring galaxies, keep this perspective in mind. Every point of light in the sky belongs to a system with its own history. Each galaxy is a chapter in the universe's long story. As we continue, it's worth spending some time on one of the most important ideas in modern astronomy: dark matter. When we observe galaxies, something does not add up. Stars orbit their galactic centers much faster than visible matter alone can explain. If galaxies contained only the stars, gas, and dust we can see, they would fly apart. But they do not. This tells us that galaxies are embedded in something invisible, a vast halo of matter that does not emit light, does not absorb it, and does not reflect it. We call this dark matter. Dark matter makes up most of a galaxy's mass. In the Milky Way, more than 80% of the total mass is invisible. The stars we see are only a small fraction of what is really there. Although dark matter cannot be observed directly, its presence is felt through gravity. It holds galaxies together. It shapes their rotation. It influences how galaxies form and how they grow. Without dark matter, galaxies as we know them might not exist at all. In the early universe, dark matter gathered first. It formed gentle gravitational wells. Ordinary matter followed, falling into these wells and forming the first stars and galaxies. In this sense, dark matter is the unseen framework of the universe, a quiet structure beneath everything we observe. Galaxies move through these dark matter halos like islands in an invisible sea. Their shapes, sizes, and motions are deeply connected to this hidden component. Even galaxy clusters depend on dark matter. The hot gas and visible galaxies account for only a small portion of their total mass. The rest is unseen, yet essential. Dark matter reminds us that much of the universe operates beyond our senses. What we see is not always the full story. Sometimes the most important influences are the quietest ones. This idea changes how we think about galaxies. They are not just collections of stars. They are structures shaped by something deeper, something subtle, something patient. And as our understanding grows, galaxies become even more fascinating. Not simpler, but richer. not fully known, but deeply meaningful. Another important aspect of galaxies is how they change over time. Galaxies are not born fully formed. They begin as small, irregular collections of gas and stars. Over billions of years, they grow through mergers, accretion, and internal evolution. Star formation does not remain constant. In most galaxies, it rises, peaks, and then slowly declines. Gas is consumed. Massive stars live fast and die young. Supernovae heat and disperse remaining material. Eventually, many galaxies enter a quieter phase. Astronomers sometimes describe these galaxies as quenched. They are not dead, but they are no longer actively forming new stars. Their light comes mostly from older, cooler stars. Elliptical galaxies are a common example. They tend to be massive, smooth, and calm. Their internal motions are random rather than rotational. Their appearance reflects long histories of mergers and interactions. Spiral galaxies, like the Milky Way, represent a middle stage. They still form stars, but at a steady, moderate pace. Their disks rotate smoothly. Their spiral arms continue to glow with young, bright stars. Irregular galaxies often represent earlier or disturbed stages. They may be small, gas-rich, and chaotic, or they may have been reshaped by gravitational encounters. Environment plays a major role in galactic evolution. Galaxies in dense clusters tend to lose their gas more quickly. Those in quieter regions can continue forming stars for much longer. Time, gravity, and surroundings all work together. No two galaxies follow exactly the same path. Each one reflects a balance of internal structure and external influence. This diversity is not noise, it is information. By studying galaxies at different stages, astronomers reconstruct the universe's long history. They compare nearby galaxies with distant ones. They observe patterns, trends, and gradual shifts. What emerges is not chaos, but continuity. Galaxies age gracefully. They transform without urgency. They change without forgetting where they came from. And in watching them, we gain a deeper sense of cosmic time, a reminder that the universe is not rushing anywhere. It is unfolding, moment by moment, across scales far larger than ourselves. As we begin to slow down and bring this journey to a close, let's take a moment to reflect on what galaxies truly represent. Galaxies are not just distant objects scattered randomly through space. They are the universe organizing itself. They are gravity at work over billions of years, patiently shaping matter into structure, motion, and light. Every galaxy we have talked about carries a long memory. From the earliest moments after the Big Bang to the quiet glow of aging stars today, Galaxies record the passage of cosmic time. They evolve slowly, almost imperceptibly, yet their changes are profound. Some galaxies are still actively forming stars, glowing with youthful energy. Others have grown quiet, their gas exhausted, their stars aging peacefully. Neither state is better or worse. They are simply different stages of a natural process. Our own galaxy is part of this story. The Milky Way is not special because it is unique, but because it is familiar. It follows the same physical rules as countless other galaxies spread across the universe. The same gravity, the same matter, the same slow unfolding of time. When we look at galaxies, we are reminded of scale, not just size, but duration. Galaxies measure time in billions of years, not seconds or lifetimes. They show us that change does not need to be fast to be meaningful. They also show us balance between creation and destruction, between motion and stability, between chaos and structure. Even the most violent events, like galactic collisions, eventually settle into new forms. Over time, turbulence fades, energy redistributes, a new equilibrium emerges. This is one of the quiet lessons galaxies offer. The universe is not rushed. Processes unfold at their own pace. Nothing is wasted. Nothing is truly still. As this exploration ends, there is no need to hold on to every detail. You do not need to remember numbers, names, or classifications. What matters is the sense of perspective. Somewhere far beyond our sky, billions of galaxies continue their slow dance. Stars are being born, others are fading. Gravity is shaping paths that will last longer than any civilization. And here, now, you are simply listening, present, aware, connected, in a small but real way, to a universe far larger than us. Thank you for spending this time exploring galaxies together. I hope this quiet journey through space has brought curiosity, calm, and a gentle sense of wonder. For now, we leave the galaxies where they are, turning slowly, glowing softly, continuing their stories. Until next time, take care and have a peaceful rest.